All right, I think we're going to get started here. So, hello everyone, and welcome to this week's Tech Talk. The Tech Talks, the Library Data Hub's Tech Talks, are a series that try to connect UI community members with topics, issues, and tools that can help them do research in this sort of digital information age. So, to that end, we have Bert Baumgaertner. I think I've pronounced it. All right, yeah. This week to talk about agent-based models. And if you guys have any questions, feel free to just shout them out when they come up or pop them in the chat. I'll be monitoring that. But other than that, take it away.
Thank you. Can we just do a real quick mic check, make sure that's okay?
I can hear you.
Awesome. Okay, so my name is Bert Baumgaertner. I am in the Department of Politics and Philosophy. I call myself a computational philosopher. I know philosophy isn't usually thought of as using a lot of sort of mathematical modeling or computational modeling, but there is sort of a subgroup of people who are interested in philosophy of science that we do a lot of work using computer models to think about a variety of complex topics. So to that end, I put together a very brief presentation because I want to spend most of the time actually just looking at a whole bunch of models, the ways in which you can use them, intended for a really, really broad audience. So I'm going to talk a little bit about some models as well as the kinds of things that we're supposed to be doing with these models and how they might differ from other sorts of approaches that you might be more familiar with. So I have exactly one slide. All the information is here. There are going to be some resources and links that you should feel free to use. There is, in fact, an online version now of the NetLogo application that I'll be doing all the demonstrations off of. So if you have a computer here, or I might even work on a tablet at this point, feel free to pull that up and play along. Before I get started on that, I just want to take a quick moment to just talk about complex systems and the kinds of explanations that these types of models are meant to help us with. So complex systems can be characterized in a variety of different ways. They might have sort of nonlinear features. The thing that's relevant for me today is the idea that there's different levels of understanding. So you might have some aggregate behavior that you're interested in studying, like how birds flock, or in the social sciences, we might be interested in aggregate behavior, like why is there polarization about some particular kind of issue? So that's at the sort of higher level. And there's at least one or more lower levels. So in the case of polarization, it's individuals who are forming their beliefs and interacting with each other. So that's at the sort of lower level. Or in the case of flocking, you have a bunch of individual birds who are making decisions about how fast to fly, how much they should turn, whether they want to be closer to another bird or not. So you usually have these two different levels that we're going to be looking at. Sometimes you have an idea of what the individuals are doing, and you want to try to predict what would happen on aggregate. You want to figure what the average phenomenon is when all you know is what the individual elements are and how they might interact with each other. And I'll have an example for you where I'm going to see if you can sort of intuit what's going to happen when I give you all the information that you need about the individuals. Other times, we don't know what the individual elements are or what the various rules are about how they interact, but we do know what the aggregate pattern is. And so what we're trying to do there is sort of generate some hypotheses for how those aggregate patterns might come about. And so in my own work, I'm really interested in looking at how does polarization about certain kinds of issues emerge from certain assumptions we have to make about how people form their beliefs, how they talk to one another, how they might engage in social media, and so on. So those are the sort of two features that we're interested in here. So I'm going to walk through a bunch of examples using the NetLogo framework. There are other ways in which you can program agent-based models. You can do this in Python. You can do this in Java. There's a whole library known as Mason that you can do this in. But I find that NetLogo is the fastest way to get into this, especially if you don't have much programming experience as a background. It's also unbelievably quick to do any kind of prototyping in. Like to this day, I still just do all of my work in NetLogo, and then I either hire a postdoc or a PhD student to be like, okay, now I need you to code this in C, because that'll be way faster, and I want to do this with like millions of agents. NetLogo is a really, really awesome program to just like do the prototyping in. And then my time is worth more than a computer's. No offense, generative chatbots. So I can run a simulation overnight, and the programming took me like maybe a handful of hours as opposed to like a week, which if you're not a proficient C programmer like me, that's how long it would take. So we're going to use NetLogo to illustrate a bunch of these models. And I've got a list here that I'm going to walk through. They're going to start with something that's almost cartoonish, to sort of give you a sense of the kind of realism you can actually build into these if you want. And some like really hardcore agent-based modelers will just like build simulations of cities, for example, and use an agent-based modeling framework to do that. And I'll start with those kinds of examples, moving more and more abstract to some examples of what's called preferential attachment, where we've almost entirely abstracted away space. So there's different ways in which you can think about space in agent-based models, depending on what your sort of explanatory goals are going to be. I'll also then show you how you can run simulations using this NetLogo framework, and time permitting, I'll walk you through maybe some of my own research about how I've used this, and I have a link there. If you have any questions, raise your hand. I'd rather have this sort of be targeted towards whatever your interests are, rather than me walking through all the cool stuff that I've done, which you will want to know anyways. But yeah.
What library like do you recommend for agent-based model for Python?
That's a great question. I need to get back to you on that one because I haven't done any kind of agent-based modeling in Python in a very, very long time. Yeah, so I don't know off the top of my head. Luke, do you happen to know maybe? No. Okay. Okay, so I'm going to start here. So this is the web-based version, and I might toggle back and forth between the web-based version of NetLogo and NetLogo that's actually on my computer. It is compatible with Mac, Linux, Windows. The web-based version is sort of nice, especially for teaching, because then I don't have to assume that anybody's had to download it and have that working. But it's unlike a lot of other programming languages, it's pretty easy. You just kind of click and play, and it works very quickly without having to do much other downloading in terms of libraries, installations, and so on. So this is a program called Ants. Is this big enough at the back, or? All right, that's about as big as I'm willing to go. So come up closer then if that doesn't work.
Yeah, we have extra chairs over there and sit on the couches, which are in a weird circle, I just noticed.
Okay, so NetLogo has this sort of nice interface. There's a visual interface over here on the right, and there's a setup button here, which I'm going to click. And what you're seeing here is a two-dimensional world. There are also three-dimensional versions that you can build if you're interested. But this is a two-dimensional world that consists of what are called patches. So this is like a checkers board, but you can decide how many patches you want. This could, I think in this case, is about 100 by 100 grid. And I'm just going to let this go just for a couple seconds. What I've got here in the middle is a kind of home ant colony. So this is the place where ants will want to bring food to. And the blue circles illustrated here are food sources. The ants are the agents. So in agent-based modeling, you typically have three kinds of entities. You have agents, and you can have a multiple number of agents. You have some kind of environment. So in this case, it's a two-dimensional grid that's going to represent a kind of surface. And then some kind of interaction, some rules that tell you how do agents interact with each other, and how do agents interact with some feature of the world, in this case, the environment. So I'm gonna let this run for a little bit. Any guesses on what you're seeing here visually? Yeah. Yeah. So what's going on under the hood, which I'll detail in a moment, is you have these ants that are following these rules for searching behavior. So when they started from home, they don't have any food in their mouth, so they're just walking around randomly. And then when they do find some food, they head directly towards home and they leave a bit of a trail. And that trail eventually dissipates. So here you can see that the trail is now gone. And so the ants are just going to be walking around randomly because they don't have food in their mouth anymore. The kinds of things that you can explore in this kind of model is you can see how the trail is sort of really, really short behind a couple ants. If I make the evaporation rate higher, in fact, I make it really high, you can see how that tail gets now shorter, right? So the idea is that as the ant is walking towards home, it's leaving behind something on the patch. It's just like an abstract little entity, right? Where the patch will get a little bit brighter in color. And if another ant happens to also go along that patch within a certain amount of time before that's evaporated, that signal gets a little bit stronger. So the ants are actually strengthening a signal to help other ants then, if they don't have any food in their mouth and they come across one of these trails, they'll move in that direction away from home. So we have a bunch of rules. Ants, when they don't have food in their mouth, will walk around randomly. Ants, when they do have food in their mouth, walk towards home, leaving a bit of a chemical trail. And we can then decide how strong that chemical trail should be, how fast it evaporates, and how fast it diffuses. Those rules are rules that are lying on the patches. So it's the environment then will say, oh, at time step 1, there's a certain amount of like chemical here. And at time step 2, I'm going to like decrease the color a little bit down into black. So we just use a kind of color scheme to represent the amount of chemical that's in that environment. There's no rules that say, hey, ants, go find the food in this top left-hand corner and report back to the center lead ant and go back home and keep coordinating that. The idea here is that each ant is actually kind of dumb. And the things that are happening in the environment are also kind of dumb. And yet what you end up getting is a really efficient search system where ants as a collective are able to locate a food source and allow other ants to quickly find that food source again to very efficiently collect that. So there's no like central intelligence, right? The idea here is that everything's been decentralized into these lower level rules that are a little bit dumber than what you're seeing at the aggregate level. Questions about this one? Got about 5 models that I'm going to go through at different sort of levels of abstraction. Then we can come back to these 2. But yeah, questions for now.
How would you validate? You have all these parameters. You have something. In this case, I can imagine you can actually set this up in the lab, but are you going to cover validation?
Yeah, this is a great place to do this for here. So in this kind of model, right, your hypotheses might be, what do I need to have the ants be able to do? And then can I, in the real world, test to see whether ants, in fact, have those kinds of capacities? So in this case, you might ask, okay, do in fact ants leave some kind of pheromones or leave some kind of chemical trail behind them? You can go check that, right? Does that chemical diffuse at a certain rate? Does it evaporate at a certain rate? So there you would be using the kinds of parameters that you have here to then test that in a kind of laboratory setting. So that would be one way in which you might validate this kind of model.
You need to make several simulations of that, right?
Yeah, so I'll talk about this a little bit more later on, but you can like run tons of simulations to then maybe get some information about how much this aggregate behavior is going to be expected. So I'll come back to that in a second. Yeah. Okay, the next model I'm going to show you is called Fire. This one also has an element of realism to it, at the very least in terms of like pictorially what you see. But we're going to start abstracting a little bit more away from space. So in this model called Fire, the little green blocks, it's thought to be like a tree or some kind of vegetation that can burn. And from the left-hand side, we sort of simulate the start of a fire. Now, in this case, it's an agent-based model. So fire is going to be the agent, and there's actually going to be 2 different kinds of agents that you have in this kind of model. You have the sort of frontline fire which are the agents that are going to be sort of trying to move forward. And they're what they're going to be doing is looking for a green patch that they could jump to in the next bit of the space. And if there isn't a green patch that they could jump to, then it goes out. The other kind of agent is what's called an ember. So that agent is still hot, but the probability of supporting a kind of fire or starting a green bit becoming a fire is much, much less. So, and you can play around with this. The primary thing that we're going to be changing here is just this idea of density. So if I make this much lower and I start this model, say like this, you'll see that there's much less green, right? There's far fewer trees on the patches. So here, the patches are really, really small, right? You can think about them roughly about the size of how big a tree would be. As we increase this, you'll have more trees. And the kinds of question you might ask here is, how dense do we have to make this environment for the fire to be able to spread all the way from the left to the right? Validation of this kind of model, similarly, right? You might look at historical information about how dense some forests are and try to see whether you can match that onto here as well. Here's what's awesome. The actual code for this is 50 lines. One of the big sort of features of NetLogo is that it comes with the interface already built in with primitives that are sitting at a really, really high level. They call agents a turtle. And if you want to make turtles do something, you have this command that just says, ask fires, where fire is the name of a particular turtle. What am I going to ask the fire? You're going to ask whether the neighbors on one of the P colors, the patch colors, is green. And if so, you're going to ignite it. What does ignite mean? You have some code here that tells you, oh, to ignite means that a patch goes from being green to now being red, where red represents what the fire is. So one of the really powerful tools of NetLogo is that the programming is at a really, really high level that you can almost use the kind of everyday descriptions that you might give someone else for how something works and coded it here. The trade-off that you make is that it ends up being slower. So if you want to have models that have like millions of agents, NetLogo is not the right place to do it. But if you're doing things within thousands of agents and you're also just doing some initial prototyping to get yourself in that sort of headspace, like how would I design this in order for us to do it somewhere else even faster? This is a great place to sort of do that first. And I can talk more about the coding with other examples. Now I got to remind myself, what's the third one I was going to do? It's going to be the segregation. Okay. So we're going to start going increasingly towards more and more abstraction. Has anybody heard of Thomas Schelling? A few nods. Okay, so this Thomas Schelling did a lot of work on different kinds of institutional organizations, and especially was doing work in the social science related to cities and how you might have something like segregation emerge or why people move around the way that they do. It seems a quite natural explanation that when you see segregation in cities or neighborhoods, right, you see like, oh, here's a community that has one kind of racial demographic, and here's another community that has another kind of racial demographic. It's tempting to have a hypothesis that says maybe they don't like each other. So the reason why you get segregation is that people don't like each other and they want to move away from people that they dislike. Schelling wanted to test out another kind of explanation. Maybe people are perfectly tolerant, people that are different from each other. They just want a certain percentage of people that they can relate with. They want to move to a place where they at least have some familiarity or similarity with those people. Same way as like your friend groups, right? You might not dislike others, but you might just want to join another set of people who are interested in agent-based modeling. So you hang out with those a little bit more. Or you might move to a place where you're like, there's other hikers around here. I want to move to a place where there's a certain number of people who are like me. So what this model does, the Schelling model, is it populates a grid. So here you can quite explicitly see the different patches in the environment. And then each of those patches is occupied by either an orange square or a blue square. And the X's give you a signal about whether there's a certain percentage of neighboring squares. So those are the 8 neighbors around any particular square, whether there's a certain percentage of the same color as you. So here we have percent similarity wanted. It's 30%, which means you need to have at least 3 neighbors who are the same color as you. So if I zoom in, this is the place where I can do this better on my own version of NetLogo. So give me a second here. So if I click in this blue region here and I inspect that turtle, you can see this blue one here in the center has 1, 2, 3, 4, 5, 6, 7 blue neighbors. So it's happy. At least 30% of its neighbors are the same as it. This blue turtle right here has 1, 2 blue neighbors. And right now we've got it set so that you want at least 30% to be similar to you. So we put an X. The X means like that neighbor's not quite happy. They would prefer to move. They would like to move somewhere else. Where can they move? Wherever there's an empty space. So we have this sort of simple rule, which is an agent sort of looks at its current neighbors, checks to see whether it has 30% of them similar to it. If not, it's going to move. And so in the simulation, what we do is we take a turtle or an agent that is not happy, and we move it into an empty space. And then we pick another turtle that's not happy, and we move it into an empty space. And each time we do that movement, we also update each of the agents to see, okay, how about the number of neighbors that you have now? So this blue agent here in the center, if all of its neighbors, not actually all, if enough of its neighbors end up moving, it might become unhappy and thereby want to move itself. So if we come back to the model, if I click once, what we do is we have each of the agents that were unhappy moved to a new location, and then we update everybody. That's right, yeah. So after they move, wherever they move from becomes vacant. That's right. And so you can click this each time, or we could just hit the go button, and the simulation will keep going until everybody's happy. And what you can see here is that there's a fair bit of segregation that seem to have emerged just from these individual level rules of people just wanting to move to somewhere else where they think that they're going to be happy. Where to be happy just means I need to have a certain number of people who are similar to me. I have the blues are like, I've got nothing against the oranges, right? I just want to have a couple blue neighbors. Things that you can play around with in this kind of model is what should the percent of similarity be? Right? We could make it 40%. Does it need to be 50%? And the other thing you can play around with is how dense does this initial setup need to be? So if I decrease the density, then there'll be a lot more spaces that could be occupied. Which means, right, here's a hypothesis. If you have less density, there's more options for people to move to, which means it probably is going to be easier to find a place where you're going to be happy, given that there's 50-50 in terms of the number of people in this group. If density is really, really high, you're going to be limited by where the open spots are, which means it might be harder for people to find places that they would be willing to stay at. So yeah, actually I can do this in a second. You can explore those two different parameters, right? You can change the similarity wanted and you can change the density of it. This kind of model is a little bit more abstract, right? Like, what exactly does the density here correspond to in the real world? You might say something about like housing availability, maybe. That's much less obvious. Perhaps easier is the idea of like percent similarity, right? You might start doing some kind of survey research to see like, okay, like how much tolerance do people have to others versus how many friends do they want to make sure they have similarities or enough sort of like hobbies in line with that they'd be willing to sort of move to get there. It's not, it's a little bit more hand wavy as well. It doesn't have this sort of like concrete metric, but the key thing that I take away from this kind of model is you get a hypothesis that is completely different than what the alternative was, right? If someone says the reason why you see segregation is because people move away from neighborhoods where they don't like a certain number of people, this one tells you, well, here's a completely different alternative hypothesis. People aren't moving away because they dislike things. People are actually moving towards things that they do like. And that hypothesis has a very different flavor, right? So in many ways, this sort of sets up a different kind of theoretical way of thinking about just the hypothesis space that you're going to be considering in the first place. So here, your job might not be about, or your interest might not be about validation at all. It just might be about exploring different hypothesis spaces. Yeah. So right now, I think this is set up as a torus, which means if you move all the way to the right, you reemerge over on the left. And if you go all the way to the top, you reemerge at the bottom. You can set this up so that there's actual boundaries if you like. And in the next one that I'm going to get to, you can even just forget about a two-dimensional grid or a three-dimensional sort of space and be like, I just want to have network structures. And you can do that instead as well. In fact, that's probably a great segue to get into this. Is that the next one? Okay. But before I do that, I want to do one fun example. Okay, so I just mentioned, right, in the Schelling model, you have this aggregate behavior and you're trying to think about what the possible mechanisms are that might produce that kind of aggregate behavior. Sometimes you can know exactly what the individual elements are and how they're going to interact, and then your guess is you're going to try to guess or predict what's going to happen at the aggregate level. So here's an example where I have a bunch of agents, which we represent as arrows. The different colors are just sort of randomly assigned. They're all facing other arrows at a certain angle. And what we're going to do is each agent is going to move forward, I think it's 0.3 units, and a unit is determined by the size of a patch, the grid. So they're going to move forward 0.3, and then they're going to rotate themselves as well. So you're going to see this as an arrow. So if we hit go, given the angle that the agent was at, given the step forward that they make, and then a readjustment of the angle, we see that they just end up following each other. And we can have turtles do what we call, they can drop a pen. So that allows you to, maybe I have to do track turtle then. Oh, right. You can barely see it actually. There's now color trailing, I think the gray one. So let's pick a different one. Here we go. Now you can see it's there's like a magenta colored one up here where we're tracking it, the circle. It'll become obvious in a second why you want to do that. But I don't want to give away the thing I'm about to do, which is this. Suppose instead of moving forward 0.35, they move forward 0.5. So we increase the step forward that they take before they turn. So each agent now, right, instead of just taking 0.35 steps forward, they're going to take 0.5 forward, and then they're going to turn. What do you predict will happen on aggregate? The angle is do this without keeping it away. They turn right 1 degree to stay on the circle.
Circle expand.
So one guesses the circle will expand, but there'll still be a circle. Fan out, maintaining a circle or not maintaining a circle?
Maintaining a circle, but if they're leaving a trail.
A spider, okay. Any other guesses? I'm going to run it without tracking the turtle. And we can also speed this up if we want, but that's worth doing. Okay, so I'm going to change the speed now. So the circle does in fact get bigger. But then it also contracts again. And it gets bigger. And it contracts again. And if we're following just one turtle, they'll end up making a perfect circle. But if we had tracked a different turtle, right, they would have drawn a circle in a slightly different location. So this is a nice example that gets used by Walensky in the textbook on agent-based modeling that they have to sort of illustrate, like, you can know everything there is to know about the individual elements and the rules for interactions. It's not always obvious how things will aggregate. Just because you know the individual or that lower level stuff does not guarantee that you're going to know what's going to happen at the aggregate. Okay, so let me do one last example before I'm happy to ask or answer any questions, run through how you can do simulations with this, and potentially some of my own work. So I'm going to run this in for a little bit, and then so that I have a picture that I can refer to. So in the study of networks, it could be social networks, it could be computer networks, there's often this feature known as like a scale-free element. So the idea here is that you have these hubs. You have like a computer that ends up being the source for a lot of information, or celebrities, right? You have one person that has a lot of fans on Instagram. But the vast majority of people, or the vast majority of computers, will have very, very few kinds of connections. So you have these kinds of network structures where we will ask, how many degrees does each node have? Where the degree is how many connections are there from that node to another node. And if you plot this like I have over here on the left, on the x-axis, you have the number of degrees. So over here on the left, these are the nodes that would have like a degree of 1. They're only connected to one other node. And then this would be like the nodes that have a degree 2. And then out here, this will be like nodes that have a degree, I think this will be like 5. Up to, and then you go way out. And on the y-axis, you just have a frequency distribution. How many nodes are there that have 1 degree, are connected to just 1? So this is known as a scale-free property. And you might ask, what sorts of things make that emerge? Like it's unlikely that we say beforehand, hey, I would like this network to have this feature of the degree distribution. Please make sure that you obey that. That's usually not intended at the beginning. So we can ask, what might lead to that kind of aggregate pattern? Preferential attachment is one possible explanation of this. And here's how preferential attachment works. We start out with just 2 nodes that have a connection between them. And we're going to introduce, you can think of this as like Instagram at the very early days. 2 people, or actually Instagram doesn't work because followers isn't, because this is going to be symmetrical. Facebook at the early days, right? You had to accept a friend request. And when you accepted it, then you became friends. So there's a symmetrical relation. If I'm friends with Luke, that means Luke's friends with me. It's not the same on Instagram, right? Instagram has followers, which might not be mutual. So at this next stage, we have a new Facebook member, and they're looking to become friends with some people. And here there's two. And so whether they end up becoming friends with this left one or the right one is the 50-50 chance. If you have a fourth individual that comes in, you see there's now 3 nodes. The 2 outside nodes have just a degree of 1. They've got 1 connection with someone. But this center node, it actually has 2 connections. So the probability that the 4th member becomes friends with the center node should be higher than the probability of making a connection with the 2 outside ones. Why? Because this center one is a little bit more popular. And you can play around with what that probability is supposed to be, right? You can weight this in a variety of ways, but in this very baseline version, it's just the number of connections that it has divided by the total number of agents. So it's a really, really simple rule. And sure enough, that center one in this round, right, ended up making that friend. So if I introduce a 5th node, probability of becoming friends with the center one is higher than becoming friends with any of the outside ones. And in this case, that was a little bit, I can redo the layout. That turned out not to be the case. They ended up becoming friends with one of the outside nodes. And so we keep doing this, right? We have this nice simple rule, like a new person comes in, what's the probability of them becoming friends with, and then you go through each of the possible individuals, and then they draw that one connection. And what you end up getting then on aggregate is this network that has these hubs and has this, what we call the scale-free distribution. Scale-free because it doesn't matter if you do this with 100 agents, 1,000,000 agents, you always end up getting the same kind of degree distribution. This is a good example of like, hey, if you have a network that has this kind of structure, let's see if the relevant mechanisms have this preferential attachment feature. Here, space is basically completely abstracted away. We don't really care about space anymore, right? This is something about network structures. Network links can represent a variety of different things. It can be friendships, it can be connections between servers, and so on. You can also, NetLogo has this really nice extension where you can build different kinds of network structures. So in the social sciences and other places where you do network analysis, people are often interested in what's called the small world property. And a small world property, between any 2 nodes, the path is going to be relatively short. So if you heard the 7 degrees of Kevin Bacon or separation, right? The idea is that between any 2 people, the number of jumps that you need to take in terms of friendship relations or who knows who is relatively short. That's known as the small world feature. Scale-free networks tend to not have that. They tend to have much longer average distances between any 2 arbitrary nodes. And NetLogo has ways of just automatically building in a kind of small world. If you just care about networks that have small world features and I want to run simulations on those, NetLogo has that kind of built in to generate these small world networks where you can then modulate how many nodes do you want to include and how small do you want that average path to be, as opposed to like a random graph, which you can also then generate each time. Okay, so what I want to do next is just show you a little bit how we could run simulations using this kind of framework, and then see if there's questions from your perspective before I maybe say a little bit about how the hell would a philosopher ever, I'm allowed to say hell in these things, right? Yeah. Why would a philosopher use these sorts of things? Okay, so the example I want to show you, or how you would do simulations in NetLogo, I'm going to go back to I have the segregation model here. I can make this a little bit bigger. So I'm back in the segregation model, and I might be interested in playing around with the different density levels and the similarity, a percent similarity wanted. I could do this by hand each time and then be like, okay, then go, and then set up, and then go, and then set up, and then go, and then change the percentage, and then set up and go, and then set up and go. And you're like, Bert, that's not a human job. That's a computer job. And you'd be right. So NetLogo comes with this really cool feature called behavior space. When I click on behavior space, I can generate experiments. So I might do an experiment here. And I want to maybe play around with the different levels of density. You might want to see how much does density matter. So I might have it do a simulation where the density is 50, and then do a level where it's 80, and then do a level of density of 95. And for similarity wanted, I might do like 25 and 33, and then I might be like, wait a minute, can't I just iterate this and like say what the start condition would be and the end condition and then iterate between that? And the answer is yes. So I might say, okay, I want to start from 20, I want to go up to say 40, and I want to increment at levels 2. This is the danger of doing this on the fly. I think that's the right way of doing that here. And then you can choose how many times you want to repeat this. So if I do 100, it will repeat that simulation 100 times. And I then need to figure out what variables do I care about? Like, what is it that I want to measure at the end of these things? So I might want to figure out whether the number of happy turtles is going, if there's a certain proportion of happy turtles at a certain number of time steps. So I might count the turtles that have, so with is a command, happy be true, and I might want to count the turtles that are not happy because maybe that's the things, those are the two things I want to compare. So it's like, oh, how do I do not, oh wait, not happy, just like Python, which is like, wait a minute, I feel like they should call it this. NetLogo is built very much with that in mind, right? If you're like, well, how do I just do negation? Put not in front of it. Done.
Can I just ask a clarifying question?
Yeah.
Are we repeating each combination of density and similarity wanted 100 times, or is this randomly sampling from the instructions you gave it 100 times?
No, this would be for every possible parameter values, like pairs, it will run it 100 times. So it'll tell you, I don't want to run this every step. Maybe I only want to run this for like 10 iterations. If I did this, oh, I didn't do that iteration off the top of my head, right? But let's say this is 20, 30, and 40. So I've got 900 runs that it's going to do based on the different parameter values that I've picked and the number of iterations for each one. So it was 3 times 3, right? Gives you 9 times 100. So I can run this. I can save it as output into a folder where this will be a CSV file. I can choose to update the views and update the plots along the way. Usually we turn these off because the visuals don't matter when you're doing these simulations. But say we kept these on, then if I hit OK, it'll just start cranking away at the simulations. And if I'm like, I want it to go even faster because I don't care about that much visualizations, you can do that. Or you can change your mind and turn them off entirely, and it's done. So that was 900 simulations of those parameter values that we did. And then I have in my folder a CSV file that's called segregation experiment table. And you can open this in Excel, or even better, just do it in R, just like you would do any other kind of statistical analysis. So I almost never do anything in Excel because if I'm running simulations that end up being in the hundreds of thousands, I don't want to do that. So I just do all my analysis in R, just like I would if I had real data. So that's one of the nice things about this. You sort of export data analysis to something else that you might be familiar with. So the fact that you have these sort of simulation features, I think, is a really, really cool aspect of this too. Yeah.
How well do you find the NetLogo program? When does it tend to fall off for you? Well,
The place where it tends to fall off is usually a function of the number of agents. And for me, I can usually handle about 10,000 for most of the stuff that I'm interested in. And then it starts to really get slowed down. There are different ways of being more efficient. So you can, in like the ask turtles command, it will like randomly sort them. And depending on what you ask turtles to do, if they're searching through the space of all the agents again, that's really inefficient. So you learn about like, no, I just need to like have it just, I got to do random pairs, right? And so if you learn how to be a little more efficient in terms of like code design, you might realize, oh, wait a minute, I can apply that here as well. So that helps a lot. But even then, I typically find somewhere around $10,000. 10,000 agents is where things start really slowing down. Yeah.
Like data, how can I estimate parameters of these models with data? It's just try and error within the parameters.
So yeah, good. Most of the stuff I've shown you here, right, is exploring the parameter space and then measuring some kind of aggregate feature. And you're asking, if I know what the aggregate feature is, but I don't know what the parameter space is, how can I do that? It's not built into NetLogo, but there is, oh man, it's been a little while. I think it's called evolutionary space, where you can set what you want the aggregate pattern to be. And then there's different kinds of evolutionary algorithms, either genetic algorithms. I think there's simulated annealing. There's a bunch of other known sort of like algorithms for searching kind of space, where it will randomly start with some kind of parameter values, see how close it got to the to whatever the goal is. So you have an objective function, and then it changes the parameter space according to how close it got to the objective function to then see if that get closer or not. And if not, then it moves in the opposite direction. So if you know things about like graded descent and so on, there are programs where you can use NetLogo to do that sort of thing as well. But that's not built into the standard NetLogo version. Yeah, I haven't used that in a while because I typically go in the opposite direction. I'm usually going from individual things, trying to figure out what the aggregate stuff is, as opposed to knowing what the aggregate is and then trying to find the relevant elements. But yeah, that does exist. Yeah.
Are there ways to export the system state across each step?
Yes. So when I ran this simulation, so there's two ways in which you can do this. So one, in this experiment that I built, you can choose to run or run whatever the metrics at every single step. You can choose to export information about the system that is of interest to you. So if you want to have like the grid size be exported, right? The number of agents, like whatever you could possibly imagine about that system, you can include, including the seeds that you use to generate the randomness. Right now, by default, it will just randomly pick the seeds as well and simulate on that. But if you're like, no, I want to be able to reproduce exactly step by step what happened in a deterministic way, you can set the seed. So you tell it, I want you to pick this seed and then run the simulation, which is helpful if you're doing debugging or you want someone else to look at that. Yeah, so you can do that as well. By default, it's just not in there because the idea is like, have it as least complicated as possible to get people in on this. Yeah, that's a good question.
How hardware aware is it? I mean, will it take advantage of like multiple CPU cores, things like that?
Yeah, good. So it will look to see how many CPUs you've got and then make a suggestion. So I think I've got 10 on this thing. So, and I think it suggested 7. I can make it use 10 if I like. This is the M1 chips on it. I have not, I know that people have used this on GPUs, but I think most of the people who are like, if you're gonna work that hard to make it that efficient, you shouldn't be in NetLogo in the first place. Going over to Python or somewhere else. And it also depends a little bit on what your model is, right? Some of these things you can do in parallel, and some things, depending on what your model setup is, you can't, yeah. But it is at least aware, I think, when I ran the simulation, right? It says simultaneous runs in parallel, recommended maximum, well, not just recommended, maximum is going to be 10, because that's all I can do here, yeah. So maybe I'll give you a real quick highlight for how I use this, my own research, and then take any other questions. And I know you want to do a survey as well. I don't know if you want to do the survey, a short survey now, maybe while I quickly load this up.
Yeah, sure. So we just have a quick 2-question survey for the people on Zoom about how useful you found this talk. And if you could minimize that on your screen, that would be much appreciated.
Minimize this.
Yeah.
Yeah.
And then we also have paper copies if you want to pass them around. One talk with shitty on the title, so you can basically do whatever you want.
So while people are filling those forms out, both online and in person, I'll maybe just give you a little bit of a background. So I do a lot of work in political psychology, because that's a place where you have people studying the various kinds of mechanisms that might lead to issue polarization, especially in political domains. So I have a collaborator named Florian Justwan, and one of the things that we did was conduct this survey study to get a sense of what people's perceptions were in terms of their friend groups and how many issues they might agree on or disagree on. And then we also tracked where people sat on the ideological spectrum, ranging from being very liberal to being very conservative. And so we have this empirical survey data that tells us something about what the network features are like, at least from the perceived aspect of the individuals and who they would be willing to listen to. So I can build a network then where the white connections are connections between people who are of different minds on the ideological spectrum. The purple lines just represent people who are on the same side of the ideological spectrum, and in particular on the left side. And then the orange is same side of the other side of the political spectrum. And I wanted to make sure that the degree distribution is going to match what the survey data is. And I also wanted to make sure that there's a certain, what we call bubble. So people aren't in perfect echo chambers. They tend to maybe have like more friends that they are in agreement with, but they still listen to others, right? They're still getting exposed to some outside information. It's not a perfect echo chamber. So we call this a bubble, and there's a certain degree that the bubble should have. So if you are completely neutral on ideology, then your bubble is about 0.5. So that means you have about 50% of people who are like you and 50% who you think are not like you. Whereas an ideology level of 2, so that's going to be on the extremes. So you're very, very liberal and you're very, very conservative. It's about 0.71. And we build these networks so they have these features corresponding to the survey data that we had. And then the research question was, suppose the belief mechanism is just this. If you hear something and you don't have any reasons to not believe it, so you don't have any contrary evidence to it, you believe it. That's it. That's the rule. Like someone says something, I don't have any reasons to think that that's false. And that person told me, like, I don't have any reason for thinking that they're like playing a game. You believe it. This really simple rule, which we ended up calling just the preference for belief. We prefer to believe something rather than maintaining uncertainty if we don't have any reasons not to. Turns out in psychology, philosophy, both as a descriptive feature as well as a normative feature. We think it's okay for people to do this. Philosophers have made this kind of argument. And so I built that into this model as well. So we seed some information into this network, and we do so randomly according to different kinds of structures that we can play around with. And then we run the simulation and we see how the different beliefs, where the belief is like, yes, I think that's true, versus no, I don't think that's true, or 0 just means I never formed a belief about this. And we tracked that to then also see whether there's any kind of pattern in terms of people's ideology. And what we discovered is that this really simple rule, based on this other empirically informed bits about how the network looks like, is enough to give you issue polarization. You don't even have to be like biased towards like confirming your prior beliefs. You don't have to be what we call motivated in your reasoning. That will make things worse. I can actually add what we call a motivated bias, which will make the polarization even worse. But the thing we were interested in was, if you ripped out any kind of motivated bias, would you still get polarization? The answer is yes. Which, from a philosophy perspective and a political science perspective, you're like, that means you can get polarization really easily. Like, people don't have to be purposely trying to exclude others, and we will still expect it. And that, kind of like in the Schelling case, gives you a very different perspective of the kinds of hypotheses that might be explaining the kind of phenomenon that are completely missed by people who are focusing on explaining things like polarization from the sort of motivated reasoning kind of perspective. And we did that here in this kind of agent-based modeling framework. The space doesn't really matter. That's just sort of like visually to give you a feel for how things look. But it's just the network structure that really ends up doing most of the driving here. Yeah.
Agenda building, like possible goals with that, or like somehow random. It's thinking like how, you know, a place like Facebook, if they cared about this issue, they could seek or random nodes that are far apart.
Yeah.
What?
Yeah. Yeah, so a few things that we played around with was, does it matter whether the network is a small world network or not? So that was one feature that we looked at. We looked at how you might start seeding things. So if you gave 3 of the beliefs to purple agents and 1 of the beliefs to an orange agent. So this is what I have as the, one of the purples got a no, and an orange, or there were 3 orange yeses. And we could play around with, you're like, wait a minute, how many different combinations are there? It's like, there's a lot. You could give like 3 yeses to an orange and a no to the purple, and then there's symmetry considerations. You're like, oh, I don't need to care about those ones. So we played around with how things get seeded, and it turns out that makes a huge difference. How things start off is one of the biggest predictors for whether you're going to get polarization on the other end or not. We didn't play around with the network structure itself, like having an external news source or there's a central source. We didn't do that. We were imagining people sharing information within a network, irrespective of how it actually got there. But that's definitely something that you could do with this model. Yeah. So there's a link to the paper in the on the slide if you're interested in sort of diving into this in more detail. But here I just want to sort of illustrate like the ways in which NetLogo and agent-based modeling gets used. You'll also sometimes hear individual-based modeling. That's usually where you don't care about space at all, or network analysis, network modeling. I don't really care. Like whatever the interesting part of the modeling is what matters to me. Yeah, was there one more question?
Is there like a sample models that you can pull out from NetLogo?
Yeah, so one of the beautiful things about NetLogo is you have this models library, and it's organized. How do I get this thing? I won't be able to. Okay. It's organized by different fields. So there's biology ones, there's chemistry ones, there's network ones, social science. So it has a huge model library that you can explore, you can do extensions of. There's disease dynamic ones in here. So the models library is really, really rich. Any other questions? My email is on the slide and will probably be part of this as well. So if you have any other follow-up questions, don't hesitate to reach out. Thanks, everybody.
Thank you.